which is a bunch of problems on string constraints, things that we learned in the last class. Once we are able to go past these problems, those ideas would get further ensconced, right? So part B of the sheet, which is like problems related to string constraints. Let me look at the first problem. Which is about a pulley like this. Another pulley like this. Pulley like this. There is a block B like this. Pulley like this. One like this, and there is a block A like this. Do you all understand what's happening here? Now given this, if the velocity of B at a certain instant is 2 meters per second downwards, velocity of B is 2 meters per second downwards, we want to be able to find the velocity of A at this instant. We want to be able to find the velocity of A at this instant. All right. Don't break your heads on the actual direction of the velocity of A. It'll come along with its sign, and that will reveal to you the actual direction of the velocity of A. So what's the harm in taking velocity of A to be, say, V like this, upwards? If V turns out to be negative on solving, that means it must be V downwards, right? Now, essentially then, this is the string. Starting from this, and this. Single string, isn't it? Single string. And I want to be able to mark the nodes and traverse the string and apply the string constraint like I did in the previous class. Right? Okay. Now if this block A is moving up with a velocity V, then this pulley, which is integral with this block, is also moving up with a velocity V? Yes or no? Now these are two nodes. They are integral with this pulley. So these nodes are also moving up with a velocity V? Yes or no? Right? So this and this, you assign V and V. How about it? This point is fixed to the pulley. What velocity will you assign to this point? 0. This is 0. Now, this node, 0. This node, 0. This is a fixed pulley. So this node, 0. Now, if B is moving down with a velocity 2 meters per second, then this pulley is integral with B. So this pulley is also moving down with a velocity 2 meters per second. So then these nodes would also have a velocity. They are integral with the pulley. They will have a velocity 2 meters per second like this. Yes or no? Now, what about this end? Because this pulley is fixed with this. So this is a fixed pulley, so 0. What about this? 0. What about this? 2 meters per second. Yes or no? In fact, if this is a single string, I don't have to bother about this. I don't have to bother about this. Or even if I did, it does not matter. This is 2 meters per second downwards. I could take from here to here and from here to there. 2 meters per second downwards for this pulley, right? Now, let me traverse the string this way. This way. All right? When I go from here to here, then velocity of this point in this direction minus velocity of the point in this direction. So 0 minus v. Right? This is a fixed length, so I don't bother about this segment. This segment is not changing in length, right? The separation between the two pulleys is remaining constant, so yes. Oh, sorry. This is, I'm sorry. See, I should have, this is also there. So this is going to be, I go this way. I'm so sorry, I missed out this way, right? So I'll go this way. So that's going to be final point, velocity in this direction, minus initial point, velocity in this direction. So that's going to be minus v, minus 0 for this segment. Then I go this way. 0, velocity of this point in this direction, minus velocity of this point in this direction, plus 0 minus v, right? I don't have to bother about this. This is a fixed length. I don't have to bother about the wrap-up length. That's fixed. Then I go this way. Velocity of this point in this direction minus velocity of this point in this direction. So 2 minus 0. Right? Then, do I bother about this? No. Then I go from here to here. Velocity of this point in this direction minus velocity of this point in this direction. So that's going to be 0 minus minus 2. Yes or no? That's as far as this segment is concerned. Clear? Then I go from here to here. This wrap-up length will not matter. It's fixed. Velocity of this point in this direction minus velocity of this point in this direction. So 2 minus 0. This anyways is a fixed length. I don't bother about this. This will be in fact 2 minus 2, which is 0. It does not matter. It does not matter, right? And all of this must add up to 0. What does v turn out to be? Can you tell me? 3 meters per second? Plus or minus? Plus. V turns out to be 3 meters per second. That means the chosen direction is right. Chosen direction is right. This? No, this is because it's given. It's given there is an attachment here. It will go down with this pulley. Okay, see, you can't, it will not make any difference. Even if you didn't take it attached. See, essentially it is attached because that's the only way this pulley has a downward velocity of 2 meters per second. How will it matter really? So what? This is this will move up and accommodate the lengths. This is a movable pulley. This doesn't have to move. The motion of this will accommodate the required lengths on either side. I know what you're trying to say. You're saying if B is fixed to this, right? When this moves down, what happens to this pulley? This stays put. Then you would wonder what happens to the lengths. Well, these lengths on these sides will accommodate the required will make the required adjustments. These lengths will vary, isn't it? When this moves down, this pulley will move up and will make the required adjustment in the total lengths, isn't it? I'll tell you, you spend some time on it before you ask questions. I think you might want to spend some time on it, Ayush. You just spend some time on it. I think that will make better sense. Otherwise, we'll waste time. You have not spent enough time on it before you are inquiring so much. Just spend some time on it. Okay, let's move on to the next problem. Did you get it right independently also? Anyone? You got right independently? 3 meters per second? And you did what I had taught? Same thing, right? So there are these two pulleys, P1 and P2. And 3 blocks, A, B, and C. Velocity of P2 is given to be 10 meters per second downwards. This pulley has a velocity 10 meters per second downwards, right? And velocity of C is 2 meters per second upwards. Velocity of C is 2 meters per second upwards. We want to be able to find the velocities of block A and block B. We want to be able to find the velocities of block A and block B. Relatively simpler problem. Hey, this pulley moves down with a velocity 10 meters per second. This pulley is integral with this mass, right? That means the amount by which this mass moves up is the amount by which this pulley P2 goes down, because it's connected to this end of the string, right? That means if this pulley is moving down with a velocity of 10 meters per second, then block A must be moving up with a velocity of 10 meters per second. Yes or no? So this is moving up with a velocity of 10 meters per second. That's straightforward, right? That's simple to check. Now, B. Take arbitrary direction. See, velocity of B, let's say, is v meters per second upwards. Clear? Now I want to take care of this string. What's the velocity that I'm going to assign to this node? No. 10 meters. This pulley is moving down with 10 meters per second, so I'm going to assign 10 meters per second downwards to this. What am I going to assign to this end? 10 meters per second. Okay. Now I traverse the string this way or this way, maintaining consistency. Okay. I go from here to here. Then what do I get? Minus 10 minus V. This is wrap-up length. Don't bother. Then I go this way. Velocity of this point in this direction is minus 2, minus 10. Yes or no? Yes or no? V then turns out to be minus 22 meters per second. That means B is moving down with 22 meters per second. That's how you get it. No? Really? Are you okay with this or not okay? If you want me to, run through it one more time, I can do so. Are you all okay with this? Explain one more time? No? I'll go over it one more time. See, if A is moving up with a velocity of 10 meters per second, then this end, which is integral with this pulley, is moving down with 10 meters per second, which is the velocity of this pulley, right? Now, this string, look at this string. It's integral with this pulley. Now, this point, this pulley is moving down with a velocity of 10 meters per second. That means these two ends are moving down with 10 meters per second. Now, I traverse the string this way. I'm assuming the velocity of B is V upwards. So, now I go this way. This is my direction of traversal. This is the final point. This is the initial point. Velocity of this point in this direction, minus 10, minus velocity of this point in this direction, V. 0. Then I go this way. Velocity of C in this direction, minus 2, minus velocity of this in this direction, plus 10. Minus 2, minus 10 is 0. Their algebraic sum must be 0. V turns out to be minus 22. That means B must be moving down with a velocity of 22 meters per second. How many of you got it right independently? Okay, okay. These pulleys unnecessarily, you know, in the figures, in the sheet, they look so fancy. It's so cumbersome to draw such fancy figures. Okay. We want to find the acceleration of the pulley, P2. This is P1, P2, P3, right? So first things first, let me deploy, even before we go ahead with constraints, let me start writing equations of motion for the 3 blocks, right? A, B, and C. First things first, suppose the tension in this string is T, right? Now if you look at the free body diagram of this pulley, just this pulley, then it's going to be T like this, T like this, and if T1 is the tension here, then if this pulley is light, then T1 is approximately 2T. Did I explain that to you in the previous class? T1 will turn out to be 2T? No? So, okay. So, if T is the tension here, then the tension in this is going to be 2T. This is 2T, 2T, etc. What would then be the tension here? 4T. If you look at the free body diagram of this, the tension in this string is going to be 4T. Now, say A has an acceleration A1 upwards. A has an acceleration A1 upwards. Then this, if A moves up by an amount A1, then this end will move down by an amount A1. That means the acceleration of this pulley is going to be A1 downwards, right? A1 downwards. Now, what would be the equation of motion for this? Let's say these masses are, this mass is M1, so M1G. So 4T minus M1G is M1A1. That's the equation of motion for A. M1A1. Right? Okay. Look at this. Mass B. Suppose mass B is M2. So M2G. And say B has an acceleration A2 upwards. Say B has an acceleration A2 upwards. Oh, this is given? Okay. If same masses, so M. That will make our computation easy. MA1. Okay. What would be the equation of motion for B? 2T. See, on B, 2T will act this way. So 2T minus mg is ma2. Now, say the acceleration of this pulley, or this mass C, say acceleration of this mass C is A3 downwards, Okay. What would then be the equation of motion for C? For C, there is mg, there is T acting upwards, and there is A3 downwards, right? So that's going to be mg minus T is ma3 for C. right? Clear? Just I felt like. It could all be cock, but eventually A3 would come out with a sign. If A3 turns out to be +5, that means my choice of direction is right. If it turns out to be -5, I don't care. Then I know it's moving up with 5. Right? I'll choose arbitrary directions. I don't want to break my heads on the actual direction of motion and waste. All right. Now, how many equations and how many unknowns? 1, 2, 3 and t. 4 unknowns, 3 equations. That means only the fourth equation must be a filler equation, which must be the string constraint, Now, how do I get past? Can I just remove all the clutter from you? MGs, etc. Now I don't need tension. All tension gone. Now I just need to deal with the string constraint. You don't like A3 downwards? I'll put it upwards. Now you're okay with it, na? All right. Now, this string constraint has already been taken care of. Why? The moment I say this is moving up with A1 and this is moving down with A1, that means I've already assumed constancy of this string length. So this first string is already factored in our string constraints. I don't have to bother. Now this string. This has an acceleration A1 downwards, this has an acceleration A1 downwards. Now this I do not know. Suppose this pulley has an acceleration A0 downwards, Now I go with this string. I apply the string constraint to this. What do I get? I go this way. Minus A1, minus A2, plus wrap up length. I don't bother. A0 minus A1, all of this must add up to 0. That's 1. Right? I need to eliminate A0. I mean, I don't want to add further plight to my game here, right? A1, A2, A3 were already there in this, and I want to stick to that. I need to eliminate A0, and therefore, I have another string that will help me eliminate A0. When I apply string constraint to this, then A0 obtained from there and A0 obtained from here will together connive to get eliminated. Right? You know what I'm saying? Okay, now let me talk of this string. This pulley, that is. When I talk of this pulley, this would be A0 downwards, this would be A0 downwards. This end is going to be A3 downwards. You're okay with this A3, na? This would be 0. Yes or no? Now, let me apply the string constraint this way. Or you can go this way. You have any specific choice, Niloy? This way, or any way is okay? This way, huh? This way. Okay. We'll custom make the solution for him. Okay, so I go this way. Then, acceleration of this point in this direction is minus A0. Minus acceleration of this point in this direction is minus A3, right? Wrap up length, I don't bother, then I go this way. 0. Acceleration of this point in this is fixed to the ground. So 0 minus a naught is 0. Right? So that gives me 2a naught is a3. So this a naught can be written as a3 by 3, a3 by 2. This a naught can be written as a3 by 2. Right? And then I can forget all about this. So this would be my constraint equation effectively. So one equation, 2, 3, 4, 4 equations, 4 unknowns. Don't waste your time solving all of this. You should know how to constitute these equations right now. Right? All's good, it makes sense? So the velocities of A and B are 1 meter per second and 3 meters per second. We want to find the velocity of the block C in meters per second. We want to be able to find the velocity of this block. Clear? It's a very ordinary case of string constraints. First of all, as far as C is concerned, it's maintaining contact with B. Now B has a velocity 3 meters per second to the left, right? So the horizontal component of C must match with the horizontal velocity of B so that they could maintain contact. So for sure C has a velocity 3 meters per second to the left. That's owing to a wedge constraint. That's owing to the fact that the blocks C and B must maintain contact. So in the horizontal direction there is no relative motion between C and B, but along the vertical direction there would be relative sliding between C and B, right? And the horizontal motion of C is not participating in the strings, is not altering the string length, right? The string length is being altered by the vertical motion of C. The vertical motion of C is instrumental in changing this length, yes or no, right? And the vertical motion of C, the vertical velocity of C is also the velocity of C with respect to B. Because B has no vertical velocity, if C has a vertical velocity V, as seen from the ground, then that's also the velocity with respect to C. Yes or no? Velocity of C with respect to B, right? Say C has a relative velocity V with respect to B, which is V like this. And this is the velocity which is instrumental in altering the string length. So when we write our string constraint, then the horizontal velocity of C will be passive. It's the velocity of C along the vertical which will participate in our string constraint equation. Do you understand that? Now, in this direction, again look at this node. What velocity will you assign along the string? 0. Along the string. This point. 0. Now, I don't have to bother about this length. Do I have to bother about this length? This length. I have to. I have to. I have to. I have to bother. See, again, you know, the velocity of this end, this node is 0 in the vertical direction. Yes or no? Because this pulley is moving to the left, it has no vertical. So this node has to be assigned a 0 velocity, which will participate in this segment. All right. Now look at this. This point, now look at this segment. This segment. This point has a velocity same as 3 meters per second because this pulley is integral with this block. So this point has a velocity of 3 meters per second to the left. What about this point? 1 to the left? Right, 1 to the left. Right? Now, this is the wrap-up length. Couldn't care less. Now, this point, again, will have a velocity of 1 meter per second to the left. Right? And this node will have a velocity 3 meters per second to the left. How about it? We have assigned velocities to every node constituting this string starting from this to this. All that we need to do is, in a sanguine manner, traverse the string with with sign consistency as mentioned, right? So I go from here to here. Velocity of this point in this direction 0 minus v plus I go from here to here 0. This separation is not changing with time between the two pulleys, so this length is maintained constant. Now I go from here to here 1 minus 3, isn't it? Wrap up length, I don't bother. Then I go this way. Minus 3 minus minus 1. What does V turn out to be? Huh? Minus 4? Okay. V turns out to be minus 4 if I were to believe Ayush. Right? Which means C is moving down with 4 meters per second. That is what it means. It means that C is moving down with 4 meters per second. Hey, but this is not the absolute velocity of C. See, C has a velocity 4 meters per second with respect to B. But C also shares 3 meters per second with B like this. Right, absolutely. That means the velocity of C is going to be 5 meters per second, as seen by a ground observer. If you are a monkey perched on B, then you would find C to be moving down with 4 meters per second. But if you are on the ground, you would find C to be moving with 5 meters per second, as mentioned. Right? Problem on string constraints. Attempt this first, please, all of you. All right, here's a system with one fixed pulley, a block, and this block moves up with is known to move up with an acceleration a naught. Is known to move up with an acceleration a naught. Find the acceleration of small m. In terms of a naught. Find the acceleration of small m in terms of a naught. Stand by. Actually, it's easy. One thing, look at this string. Look at this string. This end has an acceleration a naught. Why? Because it's integral with this block. This is 0. This is 0. Now this pulley is fixed. So the amount by which this block moves up is the amount by which this string shortens and is the amount by which this string becomes longer. So that means this end is moving down with an acceleration a naught. That means this movable pulley has a downward acceleration a naught, right? Okay. So with this second pulley, you would assign acceleration a naught and a naught like this, right? And this string, look at this string. This has an acceleration, say, a naught. And this one, of which we do not have knowledge, this will have an acceleration, say, a1 downwards. This pulley has an acceleration a1 downwards. Consequently, we will assign to this point an acceleration a1, say this end an acceleration a1, and this an acceleration a1, right? Now, let me apply the constraint to the second string attached to the second and the third pulleys. This, okay, what would it be? I go this way. Minus a naught, minus a naught. Wrap up length does not matter. Then a1 minus a naught. That's 0. So that gives me the acceleration of this pulley in terms of a naught. A1 then turns out to be 3a naught. Right? Now this last one. In this last pulley, This end has an acceleration a naught, right? This end has an acceleration a naught. This has an acceleration a1 downwards, a1 downwards. This end has an acceleration a1 downwards. And this block has an acceleration a2. This is block. This is the block. This has an acceleration a2. Now I apply the string constraint going this way. So minus a1, minus a naught. Wrap up length does not matter. a2 minus a1. All of this must turn out to be 0. Yes or no? So that gives me a2 equal to a naught plus 2a1. But a1 is 3a naught. So a1 is 3a naught. So a naught plus 6a naught. That makes it 7a naught. Right. Right?